In this video, we are going to start talking about complex numbers and how to write our answers using the imaginary unit I when we don't have any real solutions. So complex numbers, when we take the square root of a negative, that's where this comes into play. So we've been working primarily with the real number system. The real number system is actually a part of something called the complex number system, which includes imaginary numbers, which is defined as using this imaginary unit I, and I is defined as the square root of -1. So I've already filled this in, you guys, but I'm going to kind of walk through it. So basically, we want to simplify to the point where we're not using any radicals. So it's either going to be a form of I, positive or negative, or 1, positive or negative, and it alternates, okay? So square root of -1 is I squared is -1, square root of -1 times itself, which is just -1. I to the third, we can break apart into I squared and I, which we've defined up here, okay? So -I. I to the fourth, I squared times I squared, which is 1. I to the fifth, we can break into I to the fourth times I and get I, okay? So the big thing to know is that I equals the square root of -1, and we can kind of figure out the rest from there. So when we have the square root of a negative, before we were just saying no real solutions, now we're going to write our solutions using a complex number. So what we're going to do is we're going to look at this as, remember, we can break apart numbers within a square root. So -5 is the same thing as 5 times -1, which I can break that into two separate square roots. Square root of 5 times the square root of -1. And the square root of -1 is just I. Now, I usually write the I in front so that it's obvious that the I is not underneath the square root, it's outside of it. So that is how we would write the square root of -5. It's I root 5, okay? Now, this one, square root of -9, again, think about that as -1 times 9. And I can take both of those separately. So -1 times square root of 9. Well, 9 we know the square root is 3, and square root of -1 is I. So this is I times 3, or 3I. Okay, we can also break down the square roots just like we always have. Okay, so I'm going to think about 20. Well, I know I'm going to have -1, and then I'm going to break it down further. Times 4 times 5, because I know the square root of 4 is 2. Okay, and remember, I've got this 2 out front already as well. So I have 2 times I, because square root of -1 is I. Square root of 4 is 2, and the square root of 5 is not a perfect square, so we're going to leave it underneath. So this becomes 4I root 5. Okay, so this is what I was talking about with the number system. Complex numbers encompass all of the real numbers, which we're very familiar with, as well as these imaginary numbers, which involves the square root of negative values. And we can write complex numbers in this form. This is kind of the standard form for a complex number. A plus BI. A is the real component, and B is the imaginary component. So actually, we can write any number as a complex number. So for example, 2, that's a real number. So that would be the A component. And we don't have an imaginary part, so I could write it as 2 plus 0I. There's nothing imaginary about it. 4I is completely imaginary, so it doesn't have a real part, and it only has the imaginary part. So we can write any number as a complex number where we have both the real and the imaginary part combined, okay? So this is kind of getting me to realize that the A can only go with the real component, and the I has to be with the B, the complex, or the imaginary component. So if this is the real, right, I know it's real because there's no I involved. This is real because there's no I involved. So 3x has to equal 6, and then the parts with i's have to be equal to each other. So the -5i must equal the -10yi. So they want me to solve for x and y. I'm able to write two different equations, one for x and one for y. So here, x must be 2. Here, I'm going to divide by -10i to get y by itself. So the i's will cancel, and -5 over -10 is 1/2. So 1/2 for y and 2 for x to make that an equivalent statement. All right, so we have something else here called complex conjugates, okay? We're going to get into this a little bit more later, but complex conjugates, okay, are involving a complex number and the same two terms, but changing the sign. So these are called complex conjugates, okay? So we're going to give the conjugate for each one. So all we have to do is identify A and B, and we're just going to change the sign in the middle. So this one's already good. We have A plus BI, right? 6 plus 1I. So all that's conjugate would be is just 6 minus I. It's the same two terms, but change the sign. Okay, this one looks a little funky because I is over 3. You can also think about that as 1/3 I. So there's the A, there's the B. So our conjugate would be the same exact thing, but change the sign to addition. Okay, 2I. So now this one is not in the complex form, so I want to write it as A plus BI. So it's no real component, only imaginary. So then the conjugate would be 0 minus 2I, or we could just write it as negative 2I. Either one of those would be okay. Same with 6. 6 is a real number, so it doesn't have any I. So its conjugate would be 6 minus 0I, which is actually still just 6. Okay? All right, so this is kind of refreshing what we've done already here when solving quadratics. So when we got square root of a negative using either the square root method or the quadratic formula, or even completing the square, we just said no real solutions. Now we're going to give our solutions as an imaginary number if that's the case. So these are our methods for solving. If it's factorable, we're just going to factor and use the zero product property. If there's no x term, we can use the square root method, something like this. So I would just add 49 and then take the square root. If A is 1 and B is positive, completing the square is B is even, because we have to do B over 2. So if it's even, that dividing by 2 is very easy. So an example would be this. If A is not 1, but everything divides out, right? Like if I can easily make A 1 in this case, because I can divide everything by 2, and then I still have A is 1 and B is an even value. Otherwise, the quadratic formula is a great method for solving. So we're going to solve a couple, and we're going to get some imaginary answers here. Okay, but I first want to identify which method is the most efficient. So here, this one does not have a B term, so this one we're going to use the square root method. Okay, so I'm going to isolate the x squared and then take the square root of both sides. So I'm going to subtract 25, so I get x squared equals negative 25. Take the square root, don't forget plus or minus anytime you use the square root in a solving step. All right, so now this is where normally I would say no real solutions, but now we're going to give our solutions as the imaginary number that it is equal to. So square root of negative 25 is the same as square root of 25 times square root of negative 1, so that's I, and then square root of 25 is 5. So x is equal to plus or minus 5i. Those are my two imaginary solutions. Okay? All right, this one, I do have a b term, so I'm not going to use the square root method. So I'm going to write it in standard form. And then, I'm subtracting the 2x over. And then I'm just going to check, is this one easy to factor? So numbers that multiply to be 5, that add up to be 2, negative 2, not easy to factor. So I'm going to use completing the square. All right, so I'm going to move my constant to the other side and leave a blank for completing the square. All right, so b over 2 is negative 1 squared is 1. So I'm adding 1 to both sides. Factor, b over 2 is negative 1. Negative 5 plus 1 is negative 4. Take the square root now of both sides. I'm taking the square root of a negative, but we're going to write it as a complex number. So square root of 4 is 2, square root of negative 1 is I, so this is going to be plus or minus 2i. Isolate x by adding 1 to the other side. So these would be my two imaginary solutions. All right, okay, this one's already in standard form. It doesn't appear super easy to factor because 10 times 10 is 100. Coming up with numbers that multiply or add together to be -4. I'm going to go ahead and use the quadratic formula. So A here is 10, B -4, C is 10. So x is equal to -b plus or minus b squared minus 4 times a times c all over 2 times a. All right, so underneath the square root, under that my calculator here, we get -4 squared minus 4 times 10 times 10. So I get -384. So 4 plus or minus square root of -384. And this one actually is a nice perfect square, right? Oh, no, it's not. 384. Never mind. Okay, well, I want to try and simplify this guy and break it down. Well, it's even, so I know I can divide by 2, and I know I can pull out that -1, so I know I'm going to pull out an I. So I've got 4 plus or minus I, and then let's see what else we can pull out here. So 384 divided by 2. Oh, I did not type that. Okay, well 4 goes in, so let's divide by 4. So we got 96 times 4. And does 96 divide by 4? Sure does. All right, and I can keep going with that. 4 and 6, and all these 4s I can break it. Well, I'm actually not going to break this 4 because I have a pair here. So I have a pair of 4s and a pair of 2s that I can pull out. So I have a 4 and a 2 that I'm going to pull out. And then I have a 2 and a 3 I'm going to leave underneath. So we have a 4, a 2, and underneath still a 2 and a 3. All right, so let's simplify that. So I have 8i out front of the radical, 6 underneath over 20. So now this is where I want to look at these 3 values and look what goes into all 3 of those. 4 does, so I'm going to divide all 3 of those by 4. So I get 1 plus or minus 2i root 6 all over 5. So this would be our exact solutions imaginary, so we can give a solution even if there are no real solutions. Okay, that is it for 5-5.